What's the difference between a good joke and a bad joke? Timing. From punchlines to music to running to compute, 100 milliseconds makes a massive difference. Hello everyone, my name is Stephan Pieterse. Most of you should know me, hopefully. I work at BBD, a software development company. Title is a platform engineer, but we do a variety of things. But most of our daily job consists of designing, maintaining, developing systems that take thousands of requests every second. On the side, I'm in a band called The 3 Project. We play progressive metal / rock, visuals incorporated, bunch of fun stuff we're doing. I play on a hybrid kit, part of which you can see here today, and we'll be talking a little bit about that and our requirements for low latency. Some quick definitions before we get started. So latency is time from input to response, or from A to B. In the example of a car, the time it takes to get from point A to point B is its latency. Its bandwidth or speed would be how much can you fit in the trunk or how many people can you pack into it. We'll also be talking about time. So 60 seconds to a minute, 1,000 milliseconds to the second. We'll also be talking a bit about distances. I hope you're all familiar with rulers. Now, for live audio, for low latency, for it to be done well, we need response times of less than 10 milliseconds, which is not a ton. If you compare this to visual frame rates, at around 30 frames per second, you're looking at a frame time of 33 milliseconds, which is almost triple the amount of time you get for audio. If you play online games, you might be familiar with ping, which is another name for latency, and you might be aware how a high ping can absolutely destroy your experience. For doing video and audio together, if you want to do lip syncing, there's a very small window. You've got 15 milliseconds ahead of the speaker and 45 milliseconds behind the speaker. Behind is preferred as people start to get uncomfortable if they hear something before they see the lips move. Now, to calculate the latency of physical sources, which I need to do for this setup here, we have this nifty formula, which is distance over the speed of sound. So anything that's around a meter away, the sound takes about 3 milliseconds to propagate to your ears. Now, if you're sitting at a drum kit, there's a bunch of different sources coming to you at different rates. So, for example, the kick drum over here, electronic one, but if I play it, the sound from that pad takes about 3 milliseconds to reach my ears. Up higher, we have toms. These take about 1.5 to 2 milliseconds, depending on where they're positioned. And then we've got cymbals, also positioned at different places, sometimes between 1 and 2 milliseconds for the audio to get there. Now, if you're on stage with other people, you've got a drummer, you've got a vocalist, you've got a guitarist, the distance between them and their sound sources also matter. If you've got one guy standing around 2 meters away, it's 6 milliseconds for a sound to travel to me. If you're standing on the stage, speakers over there, that's maybe another 10 milliseconds it takes for that sound to reach me. Your brain has to synchronize all these up, so you're kind of playing together. Then there's a forgotten sense in music sometimes, which is touch. Now, the nerves in your body allow for conductivity of around 55 meters a second, which means if I touch my nose, it takes about 1 millisecond for that data to get there. But for my hand, it takes around 15 milliseconds for that data. For my feet, it's 30 milliseconds. So if I'm stepping on a pedal, I'm hearing it in 3 milliseconds, I'm feeling it in 30. There's a very small window of opportunity that your brain has to kind of sync everything up to know that these go together. I want to try a little crowd participation exercise. You're going to hear a click, so we're going to be playing a metronome. It's just going to go boop. It's going to go boop consistently for a couple of minutes. When it goes boop, I want you to clap. Eventually, we'll all start clapping together on the boop. Get a nice tempo going. Are you ready? Yes, you're ready. Okay, let's try it out. You guys are doing very well. If you're going ready, there's some stuff going on. So I'm hearing the click at a different time than you are. But we're all trying to sync to that sound. And now the guys clapping at the back, You hear them and you try to sync up with them. That's throwing off the guys in the front. But we do get there eventually. Now let's try it a bit different way. We're going to be introducing processing latency into the click. So same click, but then every now and then it's just going to stop, do something else, and then resume as normal. So to kind of get an idea what that would be, it would be like someone stopping in the middle of a sentence and then going on as if nothing happened after the fact. I want you to experience what that feels like if you're actually making music. It's quite disruptive. You almost feel like you're gaslit a bit because, like, I'm sure I'm clapping on the right place, but that stuff's not lining up. That's what latency feels like to our systems. Now, for the band, I'm using a very specific setup. I've got a Lenovo T530, which is probably one of the best laptops ever made still. It's running Linux Mint. I'm running Reaper Digital Audio Workstation, or DAW, for processing the sounds. Now, this setup specifically allows for me to get low latency. I'm not really interested in how much it can process per second. I'm not interested in having a ton of RAM. I'm not interested in storage. What this system has to do is it has to process that with low latency. So we're going to see what that sounds like, how it's set up, and how it's experienced. Now, in Reaper, the first thing we kind of want to do is see that the sound card and the system is set up right for low latency. So if I step here, you can hear that when I step there, the sound happens. But because of the low latency, there's only a limited window of processing. So I can enlarge the window for processing by changing the block size and the period. But every time I do that, there's a small bit of latency introduced. And eventually, if you raise this high enough, then you've got a ton of time for processing, but the sound doesn't reach you or your audience in time. And if you have to try and sync that up to a physical audio source, that is a very horrible experience for both you and me. But if we take it back down to 256, now everything is well in the world again. Now, in this specific system, whenever I make a sound with one of these pads, it travels to the brain. The brain exports MIDI into the system, Reaper reads it, and then all these drums are matched to individual tracks. These tracks have to do some processing of some sample before it gets to us again. So if I'm playing on here, I can see the kick drum doing something. If we open it up, we see these are all the effects that it has to run through at this specific time. So I've got an equalizer on here. What an equalizer is or isn't is not important right now. The point is that it's there. I can play something, make some changes, and the sound changes. Now this has to happen every time. To see what's using all my processing time, Reaper provides us with a little performance meter. So I can see all the tracks I've got open. I can see how much CPU any individual track is using. So if I want to do more stuff, I have to go to the track that's doing the most and see that it's kind of contained. So you see the one here doing the most work is the keys track. I'm going to scroll on over. Let's see what keys is doing. We see keys has also got an equalizer, but this one's moving around the whole time. Let's see if I disable this one. We see keys drops out of the running for the lead track. There's also a section over here, which is the longest block time. This tells us how many milliseconds the processing actually took and what the window is that we have to play in this case, 5.3 milliseconds. You can see as I enable this, we expect the real-time block to go up ever so slightly, but it does go up, and if I disable it, it goes down. Now, this is important for me because I have to think about sound design. If I'm playing a kick sample and I really like how it sounds, I can do the EQ, render that sample, and only play that portion. I'm effectively caching the sound. I don't have to do it over and over again. On the keys track, because it's moving the whole time, it's dynamic. I can't cache it. So I have to make sure that everything else kind of is contained within that thing's performance. Now, not only does the setup here matter, the way you're playing and what you're playing is interpreted differently based on the spacing between the notes. So I'm going to need this. Make sure I get very low latency. So I'm going to play you 3 things. The first is called unisons, which means the notes are together. So these 2 notes together, and then this note. So very simple pattern. So we kind of perceive them as doof da, doof da, doof da. But you can also now take those notes slightly further apart. Then you get what are called flams. So the same note in your brain, but different notes time-wise. You can now hear a distinction between those toms, the tlu, tlu. And that's a very small window of time that you've got to do that. For unisons, you're looking at 10 milliseconds. For flams, you're looking at 30 milliseconds. Anything over that, it becomes a different note. If you're playing different notes, I'll do quads for you now, which is just 1, 2, 3. So 4 notes. Now, as patterns, you perceive them differently based on the spacing between the notes. But as you go faster, your window of opportunity becomes smaller and smaller to get those right. And those tiny milliseconds really make a difference there. So I'm going to go unisons, flams, quads. That's it. A set speed. We go just a tad faster. Hopefully you could still hear 3 different rhythms, but they are less than 10 milliseconds apart, less than 30 milliseconds apart, and at that tempo, it's around less than 75 milliseconds apart for the quads. I lost my clicker. There it is. Now, what does that have to do with running at all? Now, when you're running, you make certain motions with your body. Now, if you're sitting and playing drums, these motions are quite small. So it's there in the wrist and the fingers, or there with the feet. If you're running, this looks quite different. And if you're running like this, there's a certain motion that you're doing. But if you're swinging your arms like this, or running like that, there's a large motion that you have to complete. So it's different muscle systems that have different energy requirements, and you can only do certain motions in a certain amount of time. In running, we also have cadence or tempo, as we do with music, but it's referred to steps per minute rather than beats per minute in running. You also have your stride length, so how far are you running with each step, and you can use these to calculate your race paces. In running, you also need to be aware of the environment you're running on. If you're running track, you can run with very high confidence that the thing you just stepped on is the same as the thing you're going to step on now. It's very smooth, it's flat, no surprises, you can look straight in front of you. On road, it's a bit different. There are some things that go unexpected sometimes. On trail running, again, it's very different. The ground is constantly changing underneath you. Rocks are loose, you have to pay attention sometimes here rather than there. And if you're running at certain thresholds, remember, if you step on something, it takes 30 milliseconds for that information to propagate through your head. You might be going down long before you notice if you run too fast or with too big a stride. Usain Bolt, arguably one of the best sprinters in human history, had this line written about him. Despite the relatively slow reaction time of 194 milliseconds, Bolt won. Now, 194 milliseconds might seem fast if you're an API, but for runners, that is completely unacceptable. If we look at the stats for this race, we see Usain Bolt did win, and he's got a reaction time of 194. Compared to the fastest reaction time, though, that's only 156. The difference between the fastest and the slowest here is 38 milliseconds. 38 milliseconds is more than enough to shift up a position for many of the other contestants. In many cases, 100 milliseconds could take you up quite a couple of positions. Usain Bolt also had a stride frequency of around 4 a second, which translates to a tempo of around 250. We can time sort of what that sounds like. So it's 4 steps for every second that passes. So this is the tempo Usain was running at, just a bit faster. This is what 38 milliseconds sounds like. Again, it's the flams. That small difference cost someone the race. Now, how does this look in distance running? Because these sprinters, they're running fast, and 100 milliseconds off the race time makes a huge difference. But if you're running for hours on end, 100 milliseconds, there's not much difference between 3 hours and 100 and 3 hours. It might still be a win or a lose, but not a massive difference. Let's look at the allegedly controversial Two Oceans Marathon. The female winners, or female finishers for the 56K, Gerda Smith and Shalmith Muriyuki. Gerda Steyn finished in a time of just under 3 hours and 30 minutes. Shalmith, 3 hours, 37 minutes. There's an 8-minute difference between first place and second place. The paces work out to around 3:44 and 3:53 per kilometer. I had to assume stride length here to make the math easy, and you don't ask a woman a stride length, that's just rude. But if you work the math out, it comes to around 191 steps per minute for Gerda, 183 for Shalmith. Per second, that's a difference in 314 milliseconds per step and 326. 12 milliseconds. The 12 milliseconds turn out to be 8 minutes at the end of the race. Let's listen to their hypothetical cadences. So here they start off, but then slowly but surely, Gerda starts creeping ahead. "12 milliseconds stacked up. Makes a massive difference if you continue doing this over time. Now, if you wanted to know what your running performance was like, we've got a ton of fancy gear nowadays. We've got smartwatches, heart rate monitors, GPSs on your back tracking where you move on the field. I'm nailing zone 2, by the way. But you don't need fancy tech to tell you what's happening. If you want to know how far you ran, you can run. And then on Google Maps, see how far that was. You can figure out what your heart rate is by counting the pulses of your heart, checking it over time. I've already shown how you can kind of gauge a cadence based on just a watch alone. Let's go back to music quick. I'm going to play you a basic drum and bass jungle beat, 100% in time, perfect. Okay, very nice, nothing special there. We're going to shift all the notes just slightly, just 10 milliseconds. Perceptually, many of us wouldn't have even noticed the difference, but you might feel I like the one more than the other. The one sounds maybe a bit more natural. But let's go all the way up to just less than 50 milliseconds on the same beat. Not a good time. So that guy clearly sounds like they need more practice, but it's a very, very, very minuscule amount of time. Now, in music, there's a related axis of correctness, if you want to call it that, which is pitch. So the notes you are playing, are they at the right pitch for the piece you are playing? We're going to shift the few notes around in a song, but we're going to shift them around by semitones. Now, semitones are the distance between any two adjacent keys on a piano or on a fretboard on a guitar. So the difference there is a semitone. We can do it with microtonal changes, but that is quite horrid. If you want to hear what microtonal changes sound like, go try and learn play violin. The song we're going to do is Twinkle Twinkle Little Star, or the alphabet song. You might know it by many other names. It's quite a common melody. First up, 100% correct. It's almost lulling you. It's just nice. Now let's make it a bit less correct. We'll do it 95% correct. We're just going to move some of the notes, 5% of them, change the pitches. It's definitely recognizable, but it doesn't feel right. It's a bit off. Let's take it down some more. Let's go to 80% correct. So as with the drums, you can kind of make out what this guy's trying to do, but maybe go home and practice a bit more. Let's put those together. That's enough. Okay. How do we treat this correctness in the computing world? Now, if you're a large cloud provider like an AWS, you might have a service level agreement that says, we promise we will do certain things, if not, you get your money back. In the case of AWS's CloudFront SLA, they have a 100% refund if their uptime is less than 95%. So 95% is the first little off example we listened to of Twinkle Twinkle Little Star. It's a very high threshold for correctness that we have in music and in their SLA. So if your service is like what that sounded like, they will give you your money back. Over the course of a month, that 95% translates to about 48 hours of downtime, which is not a lot. The chances that you'll see a contiguous 48-hour block of downtime is very, very rare. They've got alerts set up for everything. If the performance just wobbles slightly, there's an engineer looking at it because it's costing them money. In music, 95% of the course of a 3.5-minute song, you're looking at 11 seconds. I've highlighted the edge there. That's 5%. That's the amount of time you get to be wrong when you're making music before people start noticing this isn't going well. It's not a lot of time. And unlike in running, you can't average out the next stuff. If you go a little slow on this lap, you can always speed up. If you go too fast, you can slow down. It averages out. But you can't average out correctness. Once it's wrong, it's wrong. I think a world where everything was right and we had enforceable SLAs for everything would be wonderful. But unfortunately, we live in a world where sometimes 40% is enough. I hope you'll recognize that as Twinkle Twinkle Little Star. Now let's get to computers. Modern hardware is fast, like really, really, really fast. Usain Bolt runs at around 250 steps per minute. Computers go at about 3 billion steps a second, which is, it's insanely fast. It's difficult to quantify how fast that actually is. But our systems feel slow for some reason. Everything's happening fast, but it feels sluggish. This is largely the fault of us, software developers, people building on top of hardware. It's the effect of latencies cascading, small things adding up over time. Let's do a little analogy. Imagine you are going down to your local friendly grocery store. I will be going to Checkers today. I'm in Checkers. Susie is at the till. Now, Susie is extremely efficient. Susie processes a cart in 1 minute flat, always. Doesn't matter if there's 2 items in the cart or 100 items in the cart, cash or card, Susie will do it in a minute. We're going to do single queue, single till. If you do multiples, it gets confusing quite fast. And then there's another thing you should notice, which is processing time and wall time. Now, processing time is when stuff is actually happening, when Susie is processing your cart. Wall time is the time that passes on the wall, on the clock. So real wall time. It's month end, so we'll also be adding a couple of people to the line. Now, as soon as the first one goes out, we see there was a processing time of 1 minute and 1 minute passed in real life. Susie's doing everything great. But then something happens. Someone spills something in the aisle. In comes the garbage collector. The garbage collector stops everything. Queue is not allowed to move. Susie's going on a tea break. Nothing happens while the garbage collector is doing its thing. Okay, now we resume. Now we see an interesting thing. The processing time didn't change. No one in the queue moved, but the wall time rose significantly. For all of them, there's now a difference of around 7 minutes. So 7 minutes for the garbage collector to clean whatever they were doing. And there's a new person in the queue. They just arrived here, but somehow they're also affected. Now, queue resumes as normal. 1 minute gets added to everyone, and a new person gets into the queue. Something happens again. Someone's card declined. All right. Now they're rummaging around. They're looking for cash. They've got cash, but it's not enough. Okay, they found another card. Okay, tap this card. All right, the signal's bad here. All right, okay, it went through. Now it's even worse. We're still processing at 1 minute per card, but the amount of time that has passed in real life is getting worse and worse, and there's more and more people getting into this queue. That's the cascading effect of latencies. Now, the clock doesn't just stop in computing. It also stops in sports. We see this often. If someone calls a timeout, the game clock stops. But in real world, things continue happening, regardless if you're processing there or not. Now, if you wanted to measure your performance in computing systems, we've got Grafana, we've got Prometheus. We've had interesting debates recently about Dynatrace. No one's a fan. But the tools are there for you to measure your uptime, your latencies, your responses, to see what's happening in your system. But you don't even need to be that fancy. If you can't instrument something, simply log what time you're starting to do something and log what time it ended and see what the difference is there. That'll give you a good indication already of how much wall time is being spent on something. Processing time is a little bit iffy, but it'll give you a good starting point. Now, if you're building something at the scale of a Cloudflare, these cascading things add up very, very quickly, and it really matters. Cloudflare recently had an exercise where they optimized one of their proxies. It was called Pingora, I think. And in one of the subsystems, there was a call that took 3 microseconds, or 3.65 microseconds to complete. Now, there's 1,000 microseconds per millisecond. So it's really, really tiny fraction of the amount of time. They got it to run at around 0.93 microseconds per call. At their scale, 60 million transactions a second, it's 219 seconds of compute every second that needs to happen. After they optimized it, it's only 56 seconds of compute per second. But what does that mean? So if you're buying cloud infrastructure, let's say you're buying from AWS, you would need 28 core machines, 28 8-core machines to run that logic. That's going to cost you around $6,750 every month to run that logic. After that small change, you only need 7 8-core CPUs to do the same work it was doing before. That's going to set you back $1,750 a month. That is nearly 100,000 Rand a month for an imperceptible difference in what a system was doing. If you're not a big fan of money, maybe you like the environment. Running all those CPUs at a modern thermal design power of 95 watts for those cores, at 28 CPUs, you're looking around 2.6 kilowatt hours to do that processing. That's not a lot. Over the course of a year, it's just under 12 tons of coal that has to be burnt to do that work. After the optimization, we're looking at 0.6 kilowatt hours to do the same amount of work, which is just under 3 tons of coal a year. So massive, massive difference for basically something imperceptible in the code. Recently, we had a query from one of our adjacent teams about why is my Logstash and Elasticsearch so slow? We regularly use it to process millions of transactions, but in this case, it was performing very poorly. The guys had a look, saw what was happening, and they saw that for every transaction that went through, there was a small 20 milliseconds enrichment call that was happening. 20 milliseconds is not a lot, but over the course of 1 million records, it's 5.5 hours out of your day that you have to wait for this data to be processed. If you've got 100,000 tabs open, maybe you know what's going on there. But every time you're looking to switch, you're visually looking for an icon. That takes a few milliseconds. You're moving your hand, you're clicking, or you're going on the keyboard. It's a couple of milliseconds. Once it's up, you have to parse, is this the information you were actually looking for? It's tiny, tiny things that add up and fatigue you throughout the day. If you're stuck in a cycle like this, victim of shift left, you definitely recognize this. So this is the flow end to end for any one feature. And we keep trying to make development faster, which is definitely not wrong. There's a ton of things we can do, but that's not necessarily where your time is getting lost once you start measuring and looking at the subsystems. If you're doing a build, for example, committing with a message, 60 seconds, git push, 5 seconds, opening a merge request. All right, you have to log in, get your 2FA token, manually select reviewers. These things take time and they feel like they take long. Then the pipeline starts. Then you check out, you do async something else. But this flow is still continuing. You're taking 5 minutes to download dependencies, 15 seconds for unit test, that's quite nice. Integration tests take 10 minutes. And now you're uploading artifacts. It's not a lot for you because you're not stuck in this pipeline. But over the course of 100 features that you might deliver over this year, you're spending 16.5 hours waiting for integration tests, 8.5 waiting for dependencies to download. The fix here is to have less dependencies or run your integration tests at the proper time. This is slowing down the overall release. In release management, requesting a CRQ while annoying takes about 60 seconds. And then you have to wait until someone can give you a demo slot. That takes 2 days. Now you're confirming the ticket states, okay, checking up with everyone. Someone is running around looking for test data. That takes maybe an hour. The actual demo takes 25 minutes. Prepping the environment for your deploy takes 30 minutes. And then manual testing, which you're involved in, which feels annoying, takes 20 minutes. But over the course of 100, your time spent is waiting for someone else to get the demo done. The actual demo doesn't take that long. And prepping the environment for your deployment is the other thing that's taking a long time. Stuff you're not necessarily involved in, but it slows this whole cycle down. What are the key takeaways I want you to get from this? The speed at which things can happen changes what we're willing to do. If I had to walk from here to the other venue in Cape Town, it'll take me around 40 days on foot, 24 days if I'm going by horse. But if I'm going by car, it's maybe 18 hours, 2 hours on a flight. I'm not going to walk to Cape Town to have a business meeting, but I'm willing to make a week out of it. So travel over the weekend, do some things, come back. I'm also willing to go there, fly there, have a business meeting, be back home in time for dinner. We saw this with messaging. When we had telegrams or we were writing by hand, you were only speaking to certain people. There was a lot of effort in writing. Nowadays, you can get a message to someone across the world in less than a second. It changes who we're willing to talk to, what we're willing to talk about. How we speak to other people has fundamentally changed. In the 1900s, the era of silent films, every theater basically had a group of musicians and sound effect guys that were employed to make sound for what you were seeing on the screen. But thanks to progress and automation and a bunch of other things, any one of us now has the technology to do that. But their industry has forever changed. No one is hired to sit in cinemas anymore to make music. The responsibility for that, the production for that, is in the hands of a handful of companies who have all the distribution, all the production rights, essentially. In the 1990s, if you could install DOS, you were almost an intermediate. The guys at the top of the food chain, they understood hardware from end to end and understood the software from end to end. But the world that we live in has changed quite a bit, and it has grown significantly. Nowadays, even if you can't form a coherent sentence, you can get a basic app out. The average person on the street, not technical, can maintain their phone to a degree. They can install apps, they can manage it. If you know multiple programming language, you know networking, you know source control, you know ticketing systems, etc., you're probably around a high intermediate. Being even stepping into a senior is around 15 years of in-depth experience nowadays. And I don't even think there's anyone at the top of this food chain now that understands the hardware to the end of the software end to end. The difference between being first and second is getting smaller and smaller and smaller. 80% might be a distinction, but we might get to a point where even 95% is just, it's not good enough. If we look at the recent rugby game between South Africa and Italy, 2 very similar plays happened. But in the case of South Africa, the try was awarded. In the case of Italy, it wasn't. The difference between getting the ball down to the ground before they're out of touch here is a couple of frames, which is around 50 milliseconds. 50 milliseconds consistency is the difference between being champions back-to-back and not. Now, what can you do in whatever your field is to make things better? Well, first you have to understand the setup. You have to understand what are the constraints I'm working with? What are the physical limits, like when I'm running? What are the environmental effects? And then what are your performance requirements? What are you actually trying to achieve or do? Then you need to measure. You need to include as much as you can, and you have to make sure what you're looking at. Are you measuring Susie's performance? Are you measuring the garbage collector's performance? Are you measuring the overall end-to-end experience? And you don't need to be fancy to do that. Just use simple methods to start off. And then you need to tighten your feedback loops. Actually take action. Don't just say hi to someone on Teams. Give them everything they need to parse what you want and reply to you. It's a difference between getting what you want done in minutes or hours. Know when you want to cache something and when it's not appropriate. Know when automating might not be appropriate. Know when single and batch goes, and then, as our keynote speaker highlighted, eliminate things that you don't need to be done. As technical people, sometimes we do get stuck into the shiny new stuff, like we want to do bit shifts instead of divide by 2 divisions. But sometimes that's not stuff that runs once. It's not that big an impact. We're looking for things that happen thousands of times every hour, on and on and on and on. Those are the places we want to be optimizing for speed. From running to music to computers, milliseconds matter, and 100 milliseconds can make a big difference. Thank you. I see that mic going. Do we have questions? It's not appropriate.
What are some of the lowest hanging fruit for your software developers that they can improve on that?
I still think it's dependencies. I think if you understand what you're doing, you don't need to import a package like is-odd or is-even, because the function to do that, we laugh, but it's there in production code bases. What you need to do is do a modulus 2 to check, is this number even or not? But we're sometimes so driven by, I have to deliver this thing, that you don't understand what you're doing, and you're importing other people's stuff, which might have security holes. There might be performance issues there, just to get your stuff out the door. And this first one, it doesn't make a big difference. But the 10th time you do it, it really adds up. Because now you've got a bunch of dependencies. You don't know what the system is doing. Stuff is slowing down. You just don't know. So I think understanding what you're trying to do and then working through your dependencies to see what's important or not is probably the first step.
So I would assume that to be able to understand what is going on, where you're making those losses, there's a certain period where you have to reevaluate or evaluate what's just transpired.
Yes.
Now, I would assume also that that type of phase can run loose on its own as well, where you spend too much time evaluating the process instead of getting stuff done. What would you recommend to avoid such a blocker and to get things actually done?
Well, you need to define what's good enough, because there's always going to be something else to do, something more you can optimize. In the case of this, for example, I can, if I wanted to spend the time, get it down to maybe 2 milliseconds. But it's not really worth it, because there's this diminishing returns things, like the more you try and optimize this, the more work you have to do for like incrementally smaller gains. And the physical limit here is around 10 milliseconds. So I can do it in 5, but I might hit other problems. So for example, if you've got a physical source lower down on the ground, something else is happening much faster than it should be, and those two have trouble lining up. So in this case, 10 milliseconds was good enough. I'm going with 10 milliseconds. Even though it can be faster, that was good enough. So maybe your API, you have a promise of 100 milliseconds. You can always get it to 50. You can always get it to 25. But the effort in doing so, it just grows and grows. So you have to decide beforehand, I want this in 200 milliseconds, and that's going to be good enough. We're willing to spend the month that it takes to do that, instead of the 6 months it might take to get 10 milliseconds lower than that.
No, thank you.
I'm out of time. Thank you so much, everyone. Please stick around for the rest of the talks.